All right, now all seats are sold, so we can start. So, very warm welcome to the course of deep learning. This is on the screen. You see outline of the course, what we planned for this year. You see the lectures. This is sort of we updated the program. So this year we came up with, we are trying to move to the new things, to innovative things, like to put more space for transformers and for graph neural networks, and maybe for something else new, which is not fully decided yet, so that you see in the end. And the rest of the course, it goes through kind of classical points in deep learning, through some kind of common topics, but in each topic you want to go a little bit more in depth to understand what's going on, how these things work, and how we could like model this with a little bit of math, and how we could work with these concepts and methods, and to understand the mechanics. And somewhere in the middle of the course there is so it starts to be advanced, like we started talking about adaptive gradient descent methods, this adversarial robust learning, about learning representations, about latent variable models, about variational encoders. So these are also already quite established topics. Maybe they are not on the hype nowadays, but they are quite advanced, and it's, you know, the research goes in spirals, so sometimes the topics are revisited, and then another day you see, aha, okay, we could train a big diffusion model with the same variational lower bound as the variational autoencoder, and then it's doing much better than the guns which were on the hype before. Anyway, so the course is organized this way, that there is lectures and practical classes are alternating. So once in a week it is a lab where you discuss some material needed for the lab. So at the class you discuss some relevant material. The lab is presented what to do and how to do. Maybe some auxiliary stuff is presented, so which about the software, about the servers, about this what you need in practice. And then you work on it at home. So you don't need computers for the lab classes actually when you come here. This is once in a week, and then this is like every other week, and every second week there would be a theoretical seminar for which we will publish assignment in advance in a week. So tomorrow we will publish assignment for the seminar that is going to be in the 2 weeks. And you're supposed to look at these assignments and try to solve them. Ask us questions if you don't understand something in the assignment. So like unclear formulation or notation not familiar to you. And then when you come to the class in 2 weeks, we discuss solutions on the board. So that's the mode in which the course is organized. It worked great in the previous years, and I hope it will work also great this year. This first lecture that we are starting with today, it's also updated. We used to start with kind of biological, from the biological end, from the study of the brain, the neuron, synapses, and then how the pulses and everything goes in there, what is known. That's great, and it was a great inspiration for all of the deep learning and all of the AI development, and it still is. But for this course, we now chosen to rather start with kind of basics of machine learning to put everybody on the same same page in terms of terminology, concepts, and sort of to recall and systematize all the basics, so about maximum likelihood, about these sort of things. And we want to talk like straight from this first lecture, and in the lab we want to talk about generalization and how is that working, that the neural networks which have so many parameters, how it is working with them, that they are generalizing well. So we want to kind of explore and discuss this, and for that we need to cover this already, the stuff which is considered to be classical machine learning, for which you don't really need to look at the neurons and the biology. Right, okay, so this is today's lecture. This is what I said. We discuss, we kind of go quickly through the classical topics of machine learning, with the emphasis that we want to look at, like, okay, what are the training criteria? How is the maximum likelihood is working for the probabilistic models, how that gives the training criteria. And we want to discuss the difference between training and test criteria, and maybe generalization properties. So how, what is the classical machine learning approach and its view on generalization, and the bias variance trade-off is to the same thing. Right, and then like there will be a second part, then we start talking about really neurons and something like a little bit from the biological side also as well. Yep.
Maybe like Sasha would say, maybe our style here is usually that we very much like to discuss it. Yes. So anytime, please ask questions. I'll be asking questions, like I said, another assistant here. So please ask questions. Sasha will ask questions, and we are like trying to. And this is gonna be discussion. Maybe some of you have some experience with some level of deep learning, whatever. So you may have your own question on that, or you know nothing and you don't understand it. Please ask questions. Yeah, even like during the lecture, this is very much welcome.
Yes, so Jan is one of our teachers, and he is also coming to see how the lecture is redesigned and to actively participate by asking questions. So this is new. It could be a little bit bumpy. Let's see. I mean, the material and the stuff in the slides. Okay. So we start, the deep learning course starts from the shallow learning. It might look ironically at this point, but if you think of it, yeah, it's actually, that's what we need, like technically, on the technical level, that's what we need. And I'll talk about regression and classification problems, and I want to go through like how the classical stuff is training and testing is laid out, and to talk about probabilistic predictors in both cases and generalization kind of rationale in both cases. So in the regression, we assume that there is some statistical dependence between some let's say inputs and some outputs which we are measuring, and there is statistical dependence in nature is captured by, let's say, this ground truth probability distribution P star. It may not hold in real world because things are dynamic and there are no real randomness in the real world, but it's sort of our assumption to start the learning from. And what this statistical dependence could capture? It could capture like the real noises. So if you take some measurement, you usually have not measure exactly the same number every time, but it is somehow scattered due to the many noises combining and accumulating into some normally distributed error. Or it could be some other like effects which out of our control, out of the control of the experiment, so that sometimes influence the outcome, but you don't know how, you don't know the mechanism, and you don't even like have the dependence on the maybe these necessary factors that influence that. Yeah, so this can be captured by such a probabilistic dependence. Like, okay, so the simplest case of this is that, yeah, let's assume, so this is what the main, some books on regression start from. Let's assume that there is a true dependence of star and the Gaussian noise epsilon around this in the measurement. But it could be like more general than this. And okay, if you take some training abstractly, so what we like to do is to having some observations from the nature. That means we pick the dependent variable, the x, in some way, maybe randomly from some distribution or uniformly. It depends on the experiment design. And then we measure y, and this gives us like a set of these identically distributed measurements from this true distribution. And then we apply some training algorithm. We will discuss later what it could be. But at the moment, like the training algorithm should produce us a predictor. So this is what we want. We want to predict this variable y. So this predictor is now denoted f of x. In the very simple case, linear regression, so it could be linear model, as this equation there shows. Now, if you have a predictor, how do we kind of check whether we are predicting well? So what test criterion we can use? Then it depends on the application, right? If you are doing something like in the computer vision, you would like maybe to detect position of the object. So you are regressing the position of this bounding box, maybe of the two corners of this bounding box. And you know that the true object is here. Then some suitable measure of how well you are finding this position is taken to be intersection over union of these two boxes. So intersection is this, and union is that, and like this allows you to account for different kinds of errors. So here the intersection over union would be small, right? But also here the intersection over union would be small. So it is reasonable in practice, and it's adopted as evaluation criteria for this kind of methods. But if you don't have this, or maybe just for the mathematical convenience of it, it's oftentimes that mean squared error is used. So you take the difference between the prediction and the true value of y. You consider the square difference, and you look at the expectation over this true value of y for the given measurement point x. So this loss is written here for a single measurement point of x. I will need this for expanding further, but in general, for the loss function, you can think that, okay, we're going to take expectation over x as well, or the sum over the points in which we're interested to predict. So something like this. So this is now currently a function of x. So we kind of look at the loss for a single point, but and we will work with this expression, but you could then also take the expectations everywhere over this x. So one important point to discuss here is that this way of evaluating goodness of prediction, it holds for a specific given predictor, right? So if you have a predictor, we could do that, and we could say, okay, this neural network performs better than some other neural network people have proposed before. But then if we discuss about, if you want to say, so the predictor actually depends on the training set, because the training algorithm produced the predictor from that. So if you want to discuss the goodness of this prediction algorithm, of the training algorithm, then we need to do more work. So and then it depends. So yeah.
May I go back to the slide? Like maybe what I see very important on this slide is this IID assumption that we have our training set from IID. You will see it everywhere in all our algorithms we will use. You just like this is like basic for deep learning. Yeah. So this is the first thing you will see, and second, what you will see is performance. Sasha is going to say maybe this is going to be random variable, yeah, eventually. Are you going there? Or?
Yeah. Yes. Yeah.
Yeah, okay.
Well, IID in today's material is mostly for the scene that if you have some expectation of something, then we're gonna want to approximate it as a sum, right? And for that you need IID to have some reasonable approximation here. It might be also reasonable if it's not IID, but then it depends on practice, how much it is not IID and so on. Okay, so you could view it, one way to view it is that, okay, with this IID assumption we could do some math. And then what comes out of it may or may not work in practice, as usual with math. Okay. Yeah, so I want to come to the point of this like bias variance trade-off. And for that, we gotta look at how the training algorithm performs, and the result of the training algorithm depends on the training set. So for this picture, if you have one realization of this training set, you estimate such a line. If some other realization of the training set, you estimate some other line. And okay, so now let's just take expected performance. So take the expectation of this mean squared loss over the possible draws of the training data. And there is one well-known fact, the bias variance decomposition. So this mean squared error, we could expand this and rewrite it equivalently. It decomposes in these three terms. So one term is the kind of deviation of the true value from the expectation of the true value for a given x. So this then becomes like, so this square difference in the expectation, this is like variance of the data, so variance of the nature alone. It does not depend on our predictor, it's just the variance of this. So this what we observe here in the nature. And this part of the loss we cannot reduce. So this is kind of a reducible data variance part. Then there is a part which is squared bias. So it's the difference between average of our predictions over all possible training sets to the expected true value, and then squared. So this is called squared bias. So how far we are off in expectation from the true value. Yeah, so this part it can be reduced if the model is well specified. So if the model that we are fitting is in the sort of, it's capable of describing the true process accurately, and you have enough data, or actually, no. So this is expected prediction. So if our training algorithm is consistent, so that's on the expectation over the possible realizations of the training data, if it estimates the model well, then this term can be reduced. So the only prerequisite for reducing this term is maybe good training procedure that has this consistency and enough model capacity. Right, and then there is the last term, it's the variance. So this is how much the predictor changes for every different realization of the training set. So here, if you are fitting a line, maybe it varies not so much. Okay, if there are some outlier points, it will vary a lot with this mean squared error, but assume it's not the case, so then it will not be vary a lot. So if you are fitting like more complex model, it will be kind of maybe vary more. And if you are fitting like a very complex model with many degrees of freedom, it could just make a fit to all of your training points. And as a result, that if you take a different training data, if it will fit to these different training points. So as a result, it will be highly varying outcome of this predictor depending on the training data. And then we have this classical illustration here. So like underfitting, if you have not enough complexity of the model that has high bias, is some good fitting in between, and some overfitting that you have too many degrees of freedom, it could fit the noise and then will not generalize well. Yeah, are we on the same page here? Right, and then there is this also like classical paradigm that two simple models have high bias as this linear thing, and the models which are too complex necessarily have a high variance. And hence this plot is, so this is from Wikipedia, I took, so this is like bias square, it decreases with model complexity, variance grows with the model complexity. And then, okay, what you're gonna do is that you don't want underfitting, you don't want overfitting, you want then to balance the two. So stay here in the, consider this as a trade-off and stay somewhere in between. However, like this is not like very accurate, so it was a little bit naive representation of this. So in fact, this bias depends on all of the components. So it depends on the model, on the learning methods, and on the true dependence. So if the true dependence is sinusoidal, and we are fitting the model which is sinusoidal, then we're gonna be good. So it will be a good bias for that data. In this case, we can say that, okay, our model and maybe learning method have a good inductive bias in that even from few points, it is gonna generalize well.
For a specific distribution of data and that specific model?
Well, if I understand it correctly, in this machine learning and deep learning literature, like it's a combination of the model architecture and the learning technique, which facilitates some kinds of solutions. So it could be many optimal solutions to the fitting problem to fit the data, but with this combination, so even more so about the learning procedures. Yeah, we will discuss a lot about this. Mm.
Like for me, it's more like prior we can like put into either the algorithm learning or the model, which is like tells you basically like we have some intuition what your solution could look like, and you can sort of engineer it in your solution, and this gives you some inductive bias, and it's then it will reduce the variance and it will fit the data better. So this is also maybe like way to see it.
Yeah, so what I'm doing now is I'm like we are recalling the background to warm up you for this discussion. Okay, why actually SGD for some reason finds good solutions to this neural network training and so on. Yeah, so just like comment about this diagram. So this is like a not complete picture because yeah, so the bias can be small even if the model capacity is high, but the learning algorithm chooses good good parameters in the space of all possible models, and the variance can be made small by taking enough data points actually. So there are more of the trade-offs to consider here. And yeah, in fact, what this picture suggests in the end is that, yeah, okay, actually, instead of just controlling the complexity of the class of models, we want to regularize the training in some way, either by designing a suitable algorithm or maybe by explicitly favoring some solutions over the other. Well, for now, I think that would be accurate view. Okay, so that was about regression. No, not all. Yeah, so we have not discussed the training. So how actually we do the training? And I mentioned, yes, we can have, when we evaluate and we are interested maybe in the application loss. And in this case, it might be possible to okay, consider this empirical training loss on some fixed set of training data and minimize to try to fit the parameters of the model so that it minimizes this intersection over union. It could be possible, but it could be also difficult if these boxes don't overlap, right? Then the intersection over union is 0, and it's maybe harder to optimize. So if we are going to do some continuous optimization, gradient descent, it might work if you have enough data where some points are lucky so that you have some intersection and there is some non-zero gradient and you could train, or maybe it will not work very well. So there is maybe a necessity to consider some different training criterion and what it could be for regression. So for regression, we could take simply this mean squared error loss, or we have some other options, right? So one, I would say, established approach how to design training objectives is to cast this model as some estimating parameters of a probabilistic model. And a probabilistic model could actually be also a reasonable fit for this problem because we have some scatter in this y variable, so we have some uncertainty in this nature in the first place. Okay, so then why don't we model this? So we could say, our predictor will be probabilistic now. So we just, not only we give, for a given x, we give only a single prediction, but instead we given the conditional distribution of how the output is going to be distributed for a given input. And we design some parametric model of this kind. What it could be just maybe some simple Gaussian distribution where the mean is some function parameterized maybe by a neural network or a linear model. And the variance, we could keep it constant or we could parameterize it. So in this example, I've chosen to have it parameterized and dependent on the input. And then if you expand this maximum likelihood criterion, okay, so the Gaussian density is the exponent of this square differences normalized. So if you expand, if you do the log likelihood in this formulation, then we see something like sum of square differences here. If this sigma, if this variance was constant, it would match exactly to the mean squared error. Yeah, you know that. So that least squares corresponds to the maximum likelihood under Gaussian noises. But if this variance is varied, then you have here like this extra term and here kind of this adaptive division of each of the square differences. So you got some kind of different loss function, which maybe you would not invent out of your head without considering the probabilistic model. And then, okay, so if we minimize this negative log likelihood, then also maximum likelihood estimation, it is a sound method theoretically, so it's consistent if under some conditions and asymptotically efficient. So you could rely on that it's more or less good. So this is one approach. You design a probabilistic model and then you consider maximum likelihood estimation for that probabilistic model. This gives you a sound training approach. Now, yeah, so what this model can do, it could then predict some mean trend and also predict the scatter. So this could serve you as a measure of uncertainty of the prediction. So how do we actually, in general, how do we predict? So if you have a probabilistic model and then someone asks us, okay, predict what should be the, I don't know, temperature tomorrow. No, okay, temperature is a bad example, but suppose we need from this prediction just the point estimate, so just to tell us one value, then we can use the mean function for prediction, right? So like, okay, so what is the expected, well, let it be temperature tomorrow. Or we could, if this distribution is maybe not symmetric, maybe another option for prediction would be to choose the peak value, so where is the prediction is the most probable prediction. Or it may depend on the application, like, okay, what prediction you choose. So this is not important for now today. Yeah, so I wanted to focus in here on this idea of using maximum likelihood as an alternative training criterion to taking the test loss or to doing something else. You could do other things like to build a robust probabilistic model or to use some robust training function, just somehow arbitrary loss function that is less sensitive to the outliers and so on. If there are no points to discuss here, we can go to classification. I'm going through this quickly because this is like recap, right? Now I want to play more or less the same things on the classification problem to see how the classifier is set up and how the training criterion works for the classifier. So let's consider binary classification. So we have some nature, like x and y is statistically dependent, but y now is like -1, 1. So that's convenient encoding for binary classification, that we could do more expressions on that. Then how we design usually a classifier. So the most common approach is to say, okay, we're going to have some scoring function which is real valued. And then one example of that is a linear function of the inputs. And then the classifier actually is defined as the sign of the scoring function. So then when the score is negative, it's class -1. If it's positive, it's class +1. Now, when we are classifying things, we are often interested in the error rate, how often we are classifying correctly, right? So this is this expression. So it says, this is indicator function that says when the true label is different from our classification, then we count 1. And then we take expectation over the natural distribution, how often we're going to be wrong in classifying something coming from the nature. And this can be approximated as this empirical sum. So we can call it 0, 1 loss, or the error rate, if you like. For people who are familiar with statistical decision making, this can be extended to actually not recognizing the class, but making some decision. For example, this decision need not coincide with the set of classes. So it could be like, okay, give treatment to the patient or not give treatment to the patient. And there is some loss function associated to the, our decision and the true state of the patient, how much it will cost in some units, different combinations of our decision and his or her true state. Then what we are interested in is the expected loss that we are experiencing with this decision strategy, right? So that's called risk. This is to mention that, like later on, I will sometimes call this expected test loss, I will call it a risk. Now, what about training? So if it is this discrete function like that, so like sign or the other decision function, have trouble minimizing this with gradient descent or alike, right? So here we necessarily have to have some other kind of training criterion, so something, some proxy criterion. And there are plenty in classical machine learning, right? So you have, so this blue one is our test criterion we are interested in, the empirical risk, but we cannot optimize that. But we can then do different stuff. We can do, so this would be the, yeah.
Maybe it is differentiable except for one point. The only problem is that the derivative is zero. Yeah?
Yes.
Maybe some, yeah?
Yes, it's. I'm abusing the term differentiable. I mean, it's not good for differentiable optimization. Yeah, so we have like support vector machines. You have this type of loss function. So on here on the x-axis, you have the score times the true label. So if the score is positive and true label is positive, this is positive, and that's good. This is where we want to have low loss. So this is where the 0, 1 loss function is 0. If this becomes negative, we are classifying incorrectly. We want to penalize that. And then what exactly function to take here is, yeah, it's a matter of many aspects, and it has maybe some of them are more convenient than others, and some have some particular good properties. But in practice, it works with either of them. In particular, the mean squared error also works, that you are just trying to regress the true label, this plus minus 1, despite it is discrete. You can just try to regress it with the score function, and so to penalize it by the quadratic loss. That works as well. And this is what we will do in the lab for simplicity, because it has closed form solution, and it will be simpler for us. And to discuss more in detail is the logistic regression, because this is what will often reoccur in the context of the neural networks. So it is all this sigmoid function, and then sigmoid neural networks, and then the binary cross entropy for the training. So let's see what is the setup in the classical machine learning. How do we come to this? Now we upgrade our classifier to a probabilistic classifier, similar to what we did for regression. So we say, okay, we are not gonna just do a classification, we're gonna predict a probability of the label y given x. And the logistic regression model comes from the following assumption. Okay, let's assume that the log odds, so the log ratio of the probabilities for the two classes, is our score. It is a matter of interpreting the score function. If your score function is linear, then this is kind of nicely interpretable, and it gives some meaning to this score. If the score is predicted by a neural network, it can do anything, so it can be flexible. It will not necessarily okay, so it will stay the log odds of these probabilities, but it is not essential to use such a model, like arbitrary interpretation and arbitrary mapping of the score to a probability would work as well. And so here it is, on one side it's this interpretation, and on the other side some mathematical convenience. So, but this is the assumption, and if you do this, so if you make such assumption, then it turns out that the probability of predicting class 1 expresses as such a function of the score, and that's called the logistic sigmoid function. So we have the score. If it's positive, we are classifying as class 1. If it's negative, we are classifying class -1. And we are placing such a function on it, this sigmoid logistic function, which says the probability for the class 1, right? So, okay, so here is 1/2 in between. Now, if you have this probabilistic model, we can do the maximum likelihood. So we just plug in for the product of the likelihood of all data points. We take the logarithm. So this is sum of negative. Okay, so the loss is the negative log likelihood. So we are going to minimize the sum of the negative logarithms in this model, and we can expand this if you like. So this is the function, this log 1 plus e to minus z. So this is the function which is drawn here in blue. So this is the, I don't know if it's called anything, but it's the loss of the logistic regression. So for us, it's just maximum likelihood for that probabilistic model. And then if you want to classify, yes, so here we have predictive probability distribution, and we can, as a classification, we could say, okay, we're gonna predict the class which is the most likely out of the two. And it turns out to be, back again, the sign of this scores. Right, and the extension to the multiple classes is actually quite aligned with what is above. So we say we have now a finite set of classes, and we're gonna predict a categorical distribution, so kind of probability of each of the possible classes, probability that y is in each of the possible classes. For this, we need a model which says, okay, so the score will be a vector of as many components as there are classes. So kind of one score per class, and into either it's some kind of, the higher the score for a particular class, then more likely we are to predict for that class. So kind of quality of the class prediction, if you like. And the model is actually, assumption is pretty similar. So you're saying, okay, the log odds for any two classes must be a difference of these two score components. And if you assume this, then it turns out that your predictive probability distribution must be given by this softmax function. And yes, in the classical machine learning, it is this interpretation as the log odds. It's some kind of interpretable quantity, and it's nice to have the score which corresponds to log odds. And they also discuss about kind of independence of irrelevant alternatives that say something like that this log odds for the two classes, it should not depend on, I don't know, qualities of other classes which are not relevant for these two. It's like a little bit stretched, so it's rather philosophical, so it's not, it's hard to capture it mathematically. But anyway, I mean, if you say that this is our assumption for the predictive model, how it should be related to the scores, then this is the softmax function is our model. All right.
Small typo, I think. There is like this logistic regression log that should be minus in the exponent. I think. Like down.
Here.
Yeah, there should be minus.
Yes.
Yeah.
Yeah. Would you mark on some page, please? Yeah, thanks. Now, this is, if you wish to view it in the context of deep learning, this is the model that we're going to learn where the score is a neural network, right? So nothing else changes. So this is kind of directly relevant for classification. What else? Yes, so this top part here is the copy from the preceding slide. So this is the softmax thing. And then what happens if we apply maximum likelihood to this model? Then we have this negative log likelihood as the training loss. And what we can do also is we can just, if we encode the true label as this one-hot representation of a true class, that means if you have like 5 classes, we put 1, so we have a five-dimensional vector with 1 for the true class. Then we could express this loss as this scalar product between this one hot vector and the vector containing the log softmax of the scores. And this can be recognized as the categorical cross entropy. So T, this one hot vector, is a special kind of categorical distribution, which is deterministically saying the whole mass for one class. And the softmax is our predictive model, is our prediction distribution, probabilities for each of the classes, and this negative scalar product of this vector and the logarithm of the softmax is the cross entropy of these two categorical distributions. So hence it's often called like cross entropy loss for training deep neural networks. Now, if you have this probabilistic predictive model, again, what we want to do, if you want to just output a single class, we're going to go for the maximum a posteriori decision, so the class which gives the maximum predictive probability, and that coincides with the maximum score. Okay, convenient. Yeah, and we are done with classification. Anything to add?
Just repetition for everybody of you, or is it new for somebody? Have you seen this before? Yes? Sort of?
Yes, I think everybody have met this here and there, but I think it's still good to like compress it and wrap today and like focusing on one of the things that we're gonna carry on to the further to the deep learning. So the next topic is we discussed a lot about this. So we have these two kinds of losses: the test loss and the training loss, which need not coincide. But now, regardless of that, the following question arises. So in theory, we are interested in the expected loss. How are we going to perform on average on some unknown, in some unknown cases? Also, we expect them to come from the same distribution, but yeah, how are we going to really perform on average? And this we are approximating as this empirical sum of our performance on a like randomly drawn but some finite subset tau of size n. So the question arises, how good is this approximation? So if we, let's say we are testing a classifier and it has the test accuracy, I don't know, 98, 7, 2, 3, 5. We should stop somewhere, right? Because it's computed on, I don't know, 5,000 test examples. We cannot trust all these numbers here. Maybe we cannot trust even this digit there, because we are just evaluated it on some small test set. So what is its real expected performance? Or to put it the other way, can we have some guarantees on its expected performance? And what the statistical machine learning can do, it can give you sort of this kind of statistical guarantees. And how is basically, because we pick at every test example at random, we could say that the loss function for that test example is a random variable. And then this empirical sum is like a sum of many random variables, and there are statistics that apply to that. So a sum of many random variables, it tends to be normally distributed. So that the more of them you sum up, then the closer their sum is to some normal distribution. And then you could also from that you could say, actually the chance that this empirical mean is deviating from the true mean, it can be decreasing with the size of this training set, and we could have some bounds on that. And one such bound is given by Chebyshev inequality. It says that the probability that the true risk differs from the empirical risk being greater than some epsilon is bounded by this. So here we have like variance of this loss function. Maybe that's more relevant for regression sort of problems. And then divided by the number of samples and this yeah, so there is no free lunch. The tighter you want this interval, so the tighter you want to guarantee that the true risk is close to the empirical risk, then the higher will be the probability that this could be violated, and the other way around. So these are kind of guarantees that the statistical machine learning theory can give us. So the other one is Hovden inequality. Okay, so similar kind, maybe different bound in terms of it does not involve the variance of the loss, but if the loss is bounded, so for example for the error rate, so we have the loss size 0 or 1, then it's bounded, and that's conveniently applicable. Yeah. And okay, so these inequalities we will practice this in the second lab. So actually, if you measure some test performance, we could also check with these inequalities. Okay, what is our maybe confidence interval on this test accuracy? So what we can expect if we draw another test set, maybe larger one, and reevaluate the classifier, right? There will be several ways, so we will have bootstrap and this concentration inequalities to like have the experience to feel that the test performance is actually something random. That's one thing, and the other thing is actually also what important for the discussion today and in this lab tomorrow, relevant to generalization. So what happens if this tau is our training set and we actually choosing, so we are fitting the model on that training set, and we're gonna evaluate the risk on the same training set, or the loss, if you like. So then can we still have some guarantee? And we can. And this is how like the classical statistical machine learning provides some generalization guarantees. So, but we need the following. We need to kind of not only bound such a probability that the risk deviates from the empirical risk. We need to bound this probability that this does not deviate more than epsilon for any kind of predictor in the class of predictors that we are considering. So we need to have a uniform bound. So then once we are minimizing, it will be just one of these predictors, and we will know that this probability is still less than something. And here is sort of first we can consider just simple example how to such a guarantee could be obtained, and it's really simple. Here is that we just take this Hovden inequality and what I wrote here. Okay, so exists a predictor in the class where this is violated, right? So we could see it as a union of events, and then we could apply the union bound for probabilities to upper bound it with something. doesn't matter the equations. The meaning is that, okay, so if you want a guarantee for a class of functions, then here, if you had a finite set of functions, then from this approach, what follows that this upper bound grows linearly with the size of this set from which we are choosing. So what it means that if you have maybe 10 models to choose from, and we are picking the one that performs the best for our training set, then this guarantee loosens, right? So it is then the probability that we are more away from epsilon, it decreases 10 times, tenfold. Maybe, okay, so this is one way to write this bounds and guarantees. The other way, maybe more interpretable for us. So we could rewrite this probabilistic guarantee into the statement like, okay, so the true risk is not greater than the empirical risk, the stuff that we measured on our finite set, plus some kind of margin, some bound, and this inequality holds with probability or confidence alpha. And this probability is with respect to randomly chosen training set. And this bound, it depends on this confidence. So the more confidence you want to be, then the higher will be the bound. This is what the statistics could give us. There is no absolute guarantees, right? It depends also on the number of training points, or that these points we are evaluating on. Usually, typically it depends as in this fashion. So it's like an inverse proportional to the square root of the number of points for many cases. And it somehow depends on this class of functions in which we are minimizing. And here it could be different. So there are different results. Maybe you know from support vector machines, it could be VC dimension. So like, okay, so how many points in an arbitrary configurations you could partition by your classifier in all possible ways. So basically, okay, the other way to say it, if I give random labels to these points, will your classifier be able always to classify them correctly? So this number, so how the maximum number of points such that this is true is the VC dimension. And then there is also for the support vector machines, you are maximizing the margin. And then if the decision boundary is far away from the margin, it gives you some guarantees. There is also this kind of fat shattering dimension, whether you can do this separation, this shattering with also sufficiently large margin. And then you have also like a capacity measure, which does not really depend on the dimension, but on something more. So there are such bounds. And yeah, the point is that this is like the classical view of generalization. So you have the bound on the true risk. It gives you a guarantee, and this bound typically grows with complexity. It grows with complexity. Is no bound which does not. We can look at this plot. So if we increase the model capacity, the training risk for a fixed training data, it will be decreasing, right? So we can fit better and better to the training data, so the training risk could be decreasing down to 0. But what about the test risk? The test risk, we don't know where it will go. What we know is this bound. So it's not going to be worse than this bound. And then the classical machine learning says, okay, actually, we want to stop somewhere here in terms of the model complexity, that we don't want to go to the area where the training risk is low, but we have no kind of control. We have no idea of the test risk. So this is what comes out of this analysis. And then the approach is that, okay, we should minimize some kind of structural risk. It should contain the so this training loss that we are minimizing, so this blue thing. But we should add something. We should add something that measures the model complexity, not necessarily this shuttering or whatever dimension, but some kind of regularization that grows with the model complexity in some sense, that measures the model complexity in some sense, and then this would give us a good way of automatic capacity selection, such that we do not overfit.
May I like my practical take on all these multiple equations, like these inequalities and so on? You will play with it, and you will see that sometimes they are loose, they are not really very tight, and it's all fine. Maybe what is practically very important is to understand that your results, whatever you get, is a random variable. So if you report something, and you see it in most of the papers, people report single number. It's not even mean. It's just like single number, random number from your distribution, and sometimes they even don't check if their training or test set is big enough to report like what is the significance of this number. Yeah, so this is like very often you see it in various evaluations, and what we want to point to is that this is a problem, and maybe we should think of it a little bit more.
I see you are tired already a little bit, so but worry not. Now we will go to some not heavy in the math notation stuff. So now we are good with background, and we can discuss some neurons. It is unfortunately a little bit simplified. The historical perspective and what they really did and tried and how they discover it, it's also like super interesting. But yeah, we had to sacrifice something, and this is now extract of that. So what's a neuron? Yeah, the neuron inspired by the neuron by a biological neuron in the brain, but also coincidentally very similar to linear models for either regression or the logistic regression. Okay, so you just take a linear combination of the input. So these inputs could be some inputs from the photoreceptors, from retina, or they could come from other neurons. You take linear combinations of this, and this we call pre-activation. And then we apply to this linear combination some nonlinear function, which we'll call the activation function, and the result is the output of this neuron. Yeah, so it's okay. I must say there are many models of neurons. So there are many artificial models of neurons. Some of them have the time dependency, like self-feedback things, and so on. But in the what is used today in the mainstream machine learning, in neural networks, in multilayer perceptrons, it is this model. So it is a feed-forward model with just inputs, weights, and the activation function. This picture and the model like that, they started to be, so they were proposed as the computational model of the brain, and they really were planning, okay, to implement this in the computer and to do some learning like the brain would do. And at first they were modeling this with some discrete signals, and like in the brain, the signals are discrete in some sense. So they were considering the units to be firing or still, and then also every unit could be excitatory or inhibitory. That means sort of reinforce the activation here or inhibit. And the weights, I think the weights, they consider it just, okay, it's either connected or not. There was no value associated to the weight. Yet with this kind of model, you could do some logic. You could do the and or things and more. Yes, and then for the activation function, they were using the threshold, right? So the step function. Also, signaling or not signaling the output. So this is the McCulloch-Pitts neuron model. And then if you take this kind of neurons and put them into the network, then there are quite some somewhat interesting worth mentioning facts. If you have a two-layer network, like here in this picture, then you can represent any Boolean function with that. Simply because one neuron can do AND operation, and if you take many of them and then add one more output layer, which is doing the OR operation, you get a conjunctive normal form. So it will be disjunction of many conjunctions, and this is enough to represent any Boolean function. Also, you might require exponentially many neurons in this hidden layer because this conjunctive normal form can have exponentially many add-ons. So one takeaway from this is that, okay, actually there are some functions which would be more efficient to compute if you have more layers. So you could, with more layers, you could represent some functions using the maybe polynomially many neurons, which would require exponentially many if you represent them with two layers only. So there is already kind of theoretical motivation for considering deep models. Another interesting fact about this is that if you add here like a discrete time dimension, that means there is a synchronous clock, and on each clock cycle, the neuron considers its inputs and then decides whether it's going to fire or not. And then this is the output for the next time step. And there could be feedback connections also then. So then at the next time step, it could receive its own activation as well. If you consider a machine of such discrete time McCulloch-Pitts neurons, then they proved that it can simulate what? It could simulate any finite state machine, and then if it had also some memory, it could do any Turing machine, so then it could do some stuff. Next, maybe stage. And also like historically remarkable thing, the perceptron model. I think in many machine learning courses, perceptron is taught as, okay, it's a linear classifier. But it's not exactly so. It is a lot to this. And the machine that they were building, so it is also inspired by the brain, right? And the machine that they were building, that it actually had one hidden layer. So this is the diagram for, where is my cursor? For the perceptron. So this is some receptive field. They had a camera with the 20 by 20 resolution. Okay, and then this was captured, right? So okay, so this is maybe object in the scene, then this is captured in this camera, and then there was a layer mapping this 20 by 20 to the some number of hidden units, maybe 512 hidden units, and these connections were random. So as far as I figured out, that they considered these neurons having the continuous activation function already, so not just on and off, but some continuous activation function. But perhaps there was no weights on these connections from the retina to this hidden layer, but the connections were random. And the connections, they were some wires, so they just did it like this. And then there was this layer from these hidden units to kind of few of these predictive neurons. And here, I think it was densely connected, but the weights were learnable. And the weights were represented by these things. So who knows what is this this in here? Have you met like old radio transmitters and this sort of stuff? So it is a resistance which can be changed by tuning the knob. So in the old radio, you would use it to tune the volume. And they had it in this machine. And the learning was, so the learning was automated. It was also like a machine that was learning. The learning had also like electric motor attached to this to adjust the weight. It's pretty cool. And it was learning. Yeah, so they learned something like super artificial things in a super artificial setup, but it was learning. And in some proposal of this project, this Rosenblatt, he wrote, this sort of devices will ultimately be able to do language translation, concept formulation, and whatnot. And the crazy thing about this is that he was right. So, yeah?
Can I ask something?
Yeah?
What exactly meant by saying randomly connected in the next slide? Like from
Here?
the first layer, like there's 512 neurons, I would say.
Yeah.
Like, what is meant by randomly connected? Like, can you explain more about this?
Yes, so look, it is 400 neurons here in this layer, and 512 neurons in this layer. It would be too many wires to connect everything to everything. So you need to, like, okay, you need for each unit in here, you need to connect it to some random subset of pixels.
For example,
Maybe 60 pixels.
so it's 400, it's connected to 400, one is connected to 300 neurons in the other layer, not all the others.
Yeah. So it's like this, right? Or then, I don't know. Yeah, and you pick at random to where to stick it. And yeah, this was also motivated by what they knew about the brain, that many connections are random there, and they consider this essential. And these neurons, somehow they organize this in this fovea pattern, that there were more sensors in the center, and then somehow okay, actually I'm not sure about this, because you know, so he has also a theoretical paper about this stuff. And then I have not read everything, so I don't know exactly what was in the machine and what was in the theoretical paper. And yeah, so why I find this like claim and this idea fascinating is that the technology today, we scaled up these things. So we have billions of weights, and we have maybe good training algorithms, but the architectures for these AI models, they are quite plain. So it's just some layers of this multi-layer perceptrons with these neurons. Okay, with self-attention. No, fine. But it turns out that you don't need much more to achieve already quite a lot of this. Okay, now so multi-layer perceptrons. So let's consider a deeper network of this. And already for a two-layer perceptron, we have sort of equivalence result to that statement about the Boolean networks that I've mentioned. There is the theorem saying that if you have a smooth function mapping this unit cube to real numbers, then you could approximate any such function with a neural network with two layers and with sigmoid activation functions to arbitrary precision. Yeah, it sounds like a cool result. So this is a universal approximation property. We can learn anything, but it has also downsides. It's you know what? Polynomials are also universal approximators. With polynomials, you can also approximate any function. But for some reason, it turns out that neural networks are better suitable for the practical tasks. And for some functions, it might require like exponentially many of these units in the hidden layer to approximate well some function. There are, however, some other universal approximation theorems, which are dual in the sense that they are restricting the width. So this one says, okay, the depth is restricted to two layers, and then the width of the network, so how many hidden units can be unrestricted, and then you could approximate any function with that. So these other results, they are of this dual kind that let's restrict the width. Maybe the width is, I don't know, some minimum number of neurons they need, but the depth can be anything. And that can also, was proved to also be universal approximator. Maybe one more remark about this, so that once we fix a network architecture, so in practice when we design it and train something for that, then of course it then is not a universal approximator anymore. So after we fix the architecture, it limits the expressive power of that model. So it describes some model, some class of models. And yeah, so on this theoretical side, we have this universal approximation theorems, and we could use large models to learn whatever. But coming back to this generalization discussion, if we use more parameters and more capacity to allow in these models, what about generalization guarantees? So how can we hope that we will not simply overfit to the training data? So this is the question people were puzzled a lot with, and today we can discuss one paper. It is called "Understanding Deep Learning Requires Rethinking Generalization." So this is illustration from that paper. This is the experiment they did. You take a network with 100,000 parameters, and it is applied to a data set that has only maybe 50,000 images of size 32 by 32 pixels, 10 classes, if you like to know details. And this network is trained with stochastic gradient descent, like the usual practice in deep learning, with some regularization and maybe some augmentation, also as a usual practice. And if it works well, so it achieves 95 accuracy, measure it on the test set, so it does generalize, and it works. This was already known, right? Now, the experiment that they are doing is that, okay, they say, we're going to do some capacity tests. So actually, what this network can represent. Does it have, how much capacity does it have? And it turns out that this network has quite enormous capacity in the sense that if you just assign random labels, not this, so not image of bird with a label bird, but with like any arbitrarily out of these 10 classes, it turns out that the network can still fit the training data perfectly. So these are kind of training loss versus so training iterations and then the training loss. And you see with the true labels, it trains fast and achieves 0 training loss. So it's like fully fits the training data. If you put random labels inside, it takes longer, but it still fully fits the training, all your these random labels. Yeah, so what it tells us is in the context of this complexity of the model class, which was measured by this shattering dimensions of how many data points your model is able to fully separate if the labels are random. So in this case, it turns out this is huge. So it can arbitrarily separate all of this training data, and then therefore all these generalization guarantees which were obtained by this kind of reasoning, they would be fully vacuous. So you have no idea what's going on. So you have no control over this generalization. And yet, if you give it the true labels, it predicts well, but it has this enormous capacity. So they did like few other experiments. Okay, what you can also do, you could just reshuffle pixels in all images the same way, or in every image reshuffle pixels differently. So these plots, what's that? Random pixels, sorry. What do I do? Okay. Yeah, so one of these lines is this reshuffled pixels. The other one is the random pixels. That means independently in every image they are reshuffled, and the network could still learn that. So whatever you do with the data, it could still learn to perfectly classify everything. It makes no sense, of course, because it's some garbage which we are putting for training, but it tells that it has the capacity to learn that as well. So it's not, there is no any capacity control really in the model or the training algorithm to prevent it for doing something bad, and yet it does something good if you provide it with the training data. Yeah, so this is like some phenomenon, something puzzling about the neural network, and we will have a lab to like discuss this a bit more. We will discuss this double descent and dig into the modes in which this could be working. And what we will do in the lab is actually similar to this model, that we will have one layer which will be random and many hidden units. And then we will have one predictor neuron, which will be, for which we will use the L2 loss. So we will solve it with the rather like classical linear regression approaches than with the logistic regression, because that will be simpler and we will have some analysis. So we will see what happens in this case. And we will see that in that case, it's possible to actually pump up this hidden layer without any limits, and to yet have a good behavior in terms of generalization and regularity of the solution. Yeah, okay, so that was it for today. You are still welcome to discuss these generalization things. for instance.
We should be surprised now, yeah? Like we are like we spent 1.5 hours like telling you this is not gonna happen, and then it happens, yeah. So it's surprising.
Yeah, so here I'm not showing yes what happens. It's still it's an illustration for this huge capacity, right? So it can fit everything.
These days we have like billions of parameters models. You see these large language models, and they sort of generalize. Yeah, they are not like producing garbage. We can say they are reasoning. We can discuss that, but but they are doing something meaningful. Let's say, yeah. And they are not overfitting in a way. Yeah? So this is like stretch.
Yeah. Yeah, well, so for the reasoning and the language models, we will not tell you much. We will tell you about like the building blocks, so the self-attention transformers, maybe some simple examples, but yeah, so we don't really know a lot about details about the what they do with the large language models. So they have this reasoning blocks and the reinforcement learning things. But it's even pre-trained just to predict this next token. They are already sort of recalling the right information and telling you the relevant things quite well. And then yes, there is no any reasoning built in, maybe in the earlier models. But then you ask it, okay, can you explain? Can you reason? And it does. So. Hmm?
Just by predicting the next token, somehow kinda.
The training, yeah, the training is like that.
What we will get here is not really understanding why this helps, because I think nobody knows really. But you should get some deeper understanding why this is happening, and more like details like what's inside it, what works, what doesn't work, and really going like deep into these models, how they are trained these days, and what is behind, and then you should be able to judge yourself, and maybe you come with the next explanation why it is doing what it's doing, yeah. But we have to go really deep if we want to say this. You can't just like have, okay, you have this box which creates next token and it does that. It is reasoning. Is it? I mean, why? Yeah, and you have to go deep.
I'm just saying that neither we teachers know this in depth, nor we are including this in the course. In the course, we have this different small things which are elements of this neural networks and training technology, all these normalizations, initializations, and this sort of bits. And yeah, we will cover the architectures and what we understand about these architectures, but not then these high-end things. Okay, so the more information about the course, like organization, details, credits, exam, and so on, will be discussed at the lab tomorrow. We'll see you at the labs. Thank you.